said that live variables analysis is not used for dead code elimination, but live variables analysis is used for something else, namely register allocation. And recall, a variable is live if its value may be used in the future. So let's see if this B here, it's defined at the call, so it has a value from the beginning, of course, and then here it is used, so it may be used, and after this return, well, it may still be used, so it is used for most of the program. This A is used here, but this is a different value of the A. So actually oops, something happened. The range in which A is live is this part, and then another range is this part. Okay, and what we should do is to do register allocation is to see which variables should absolutely not be assigned to the same register. I mean, we cannot put all variables in the same register clearly, and which ones cannot share a register. Well, it is those which are live at the same time. So A and B, they are live at the same time, so they cannot share a register. But I mean, this is very obvious. But C, it is not. I mean, the A, its lifetime ends here, since there is another lifetime for A there. So, in fact, A and C, they can share the same register. So this add may look like this. Add R3 and say that's the destination. And say the parameter is in R3 and R4. And then it can be R3, R4. And now we check if R3 is used and do something with R3. And now at this point, well, it doesn't matter for code execution time, but this is R4. I mean, it should be, since it was there from the beginning as a parameter. But in fact, this A could use R4 or it can use R3. It doesn't matter, since we have already touched R3, so to speak, so we have already done something with it. Well, it doesn't matter, because this register is such caller save register, meaning that if the function which called H is interested in the value of R3, then it has to save it itself. It may be destroyed at the call. Okay. So that's the idea of liveness analysis, to find which one cannot use the same register. And that is done by inspecting. Well, first of all, we need the control flow graph, and then we check which variables are used and which are defined in that basic block. I do not want to go into the details about this, because it will be, I mean, it's already a lot. And what you need to remember is that variables that are not, variables that are used at the same time cannot get the same register. And we should create a graph which contains this information. Okay, that's sufficient to know. So forget about this. But from this, we can create a graph and say these variables cannot. I mean, if there is an edge between two variables in this graph with variables as nodes, then they cannot get the same register. Okay, And so we create this graph called the interference graph, and then we try to actually do a graph coloring of this. But the goal is not to find the optimum, since it's an NP complete problem, and even though, say, we have 32 registers and we have thousands of nodes and edges, then the optimal coloring, the fewest number of different colors, it may be, for instance, 70, and that doesn't help us since we have only 32 registers. So what we do is heuristic coloring, which is efficient, and this one was also invented at IBM, and it's used in most compilers and has been in for many years, although it was patented by IBM, but I suppose several compilers other than IBM compilers also used it. That's my guess. Okay, so what do we do? Well, basically what we can do is to remove nodes which have fewer than the number of colors available as neighbors, since even if we color each neighbor with a different color, there will be one color left for this variable, for this node. So we can simplify the graph and put the nodes with fewer than the number of available colors on a stack. And eventually this graph may be empty, and then we can pop the stack and insert all the nodes again and assign them different colors. We will not go into the details of that either, but which, or not which, but how many colors are needed for this? Well, it looks like 3. Since here we cannot use only 2. But, okay, so, well, it is this 3, but can we use fewer? Well, you may pause now and think for a while to see what we can do to use only 2 colors. And assuming you have want to continue, I will continue. This assignment makes D and C have the same value, obviously. At least they have the same value just there. And since there was no other edge between these two, we can merge them into one. But this is not always possible, but that's often possible. Okay. Okay, this is more about how this simplification of the interference graph is done, but read it if you are curious, otherwise skip it. But this is more important, and namely, if the coloring fails, then it will do something called spilling, and that means a variable that is not allowed to get a register will be put in memory. And that's a problem if we have too many variables, or well, basically that. And of course there are edges between the nodes in the graph. Then it is not possible to to find the coloring. So therefore there can be spilling, and that can cause degraded performance. Okay, what we do then, if we spill code, we still have to produce correct code, and say we want to spill A and put A in memory and B and C in registers. What we do then is to introduce a new variable that is only used at that location, and then a separate for the usage of A here. So this T2 will be read from memory. That should not be A, that should be C. Okay, and now it is simpler to color this new program, since it's not the same node that is used in both this. It's only, I mean, it's T1 in this place and T2 in the other, so it's simpler to color it. And eventually the coloring will always succeed. A few iterations, usually it's only one iteration of this coloring. We have to redo the liveness analysis and construct the interference graph, but it's usually at most 3, sometimes more, but not very often. So this is a very efficient